Welcome back. In today's video, we want to transform the following sinusoidal currents into their phasor counterparts. So let's start with our current IF1 or ITF1. So that is equal to, so I'm just going to call that 1. That is equal to an amplitude of 10 sine of omega t plus an angle of 75 degrees. Here we have our sinusoidal current in the sine form, and when we're dealing with phasor domain, or when we're working in the phasor domain, we adapt the positive cosine reference. So we adapt a positive cosine, or a cosine with a positive amplitude. So that we would have to use the trig identity. So cosine of x is equal to, and this will be plus or minus sine of x plus or minus 90. So we see that we have a positive sign, so we subtract 90. So we end up with a cosine of 8t, subtract 90, we get minus 15. So we can then go ahead and use the trig identity, or not the trig identity, the relationship between the phasor domain and the time domain. And just like our complex review of complex algebra, so that would be that a cosine function, or a sine x of t, a function x of t equal to an amplitude of a in the positive cosine form. A is positive, so cosine of omega t plus theta, or we've been using phi, so let's use phi, can be transformed to the phasor domain. And in the phasor domain, that would equal to, so x, which is the phasor counterpart of the signal cosine of, well, so that would have been, say this signal is equal to x of t equal to that portion of it. Then in the phasor domain, the x would equal to, so the phasor counterpart of x of t would equal to a, amplitude a, or the magnitude a, times the complex exponential e to the j phi. So by using that identity, we can then go ahead and write this. We keep our magnitude, or the amplitude, which is 10, and write that as the complex exponential. The angle is negative, so that would be negative j times 15 degrees. We can use our shorthand notation to write that a magnitude of 10 and an angle of negative 15 degrees. And that's for our signal 1. So for signal 2, IT of 2, that is equal to a negative 17 as a cosine omega t minus 25 degrees. And that's in ampere. And that's the phasor. This is the time domain. So let's just, well, it's not x of t, I of t. So here we have a negative cosine, and we need to convert that to a positive cosine. So we're going to use the trig identity that our cosine, so basically this identity is basically shifting. Whenever we converted our sine to a cosine, all we did was advance the sine signal by 90 degrees. So we shifted that sine to the left and it became a cosine. So now to get this to a positive sine, we're going to advance that by 180. So that's cosine of x equals minus cosine of x plus or minus 180 degrees. So here, our angle is negative 25. So we're going to want to use a positive cosine, a positive angle. So that means when we use our positive angle, our negative cosine is going to be a positive cosine. Keep our omega t, and 180 minus 25 is 155, so we end up with a positive angle of 155 degrees. We then go ahead and use our same time domain phasor domain identity to convert that to the time domain, well, to the phasor domain. And in this case, we're not going to write it as a complex exponential. We're just going to skip that and write it as the shorthand notation for numerical solutions or numerical calculations. And that will end up with a magnitude of 17 and an angle of 155 degrees. That's in amperes. So that's the phasor component for that following signal. So now we move on to signal 3, I of t, and that's equal to 8 cosine omega t, so that's 6t minus 45 degrees minus a 5 sine omega t, which is 6t, and I can just put a plus phi in there, plus 0. Doesn't matter what you want to do. The angle is 0 in this case, so I can put a 0 in there. So we can then go ahead and we can work on one part of the expression at a time. So let's work on the rightmost part of the expression. So we could skip this. We can skip all the, what you would call it, all the unnecessary steps if you know the identity between the phasor and the time domain, and that is a signal x of t. So let's just write that out. A signal, let's use a different color. So a signal x of t is equal to a signal a sine of omega t, and we can transform that into the phasor domain. We end up with the phasor counterpart. X equals a times the complex exponential e to the j pi over 2, which is equal to minus j times the magnitude. So we could do that, or we can just work on the cosine part of this. So we can say we have a minus sign, so we can use our trig identity and convert that to a cosine, because we can use our following identity. So we have a minus sign, and our angle in this case, we're going to call our angle a positive angle. So we're going to minus 90. So we go ahead. So that's going to be a positive cosine. Change that to a positive 6t minus 90 degrees. So then if we use Euler's identity, which we're going to use, been using, so it's equal to cosine theta plus j sine theta. We then go ahead, and cosine minus 90 is going to equal to 0, so that goes away. So cosine minus 90 is equal to 0. And then if you use cosine minus 90, we get positive 1. So we can go ahead and write that as positive 1, but remember our j, so then this would be 5 times j. Or normally, I would write that as j5. So now we can deal with this part of our expression, and we can use Euler's identity to deal with that. And basically what we can say is that we're going to end up with 8 times cosine minus 45 cosine of minus 45. Then we know we're going to have a imaginary portion. So then we can go ahead, and that imaginary portion is going to be negative because our angle is negative. So that's a negative j sine of minus 45 plus j of 5. And we're going to keep our 8. We can factor out the j's. And by doing so, we get, let's just do that. So 5 of minus 45 minus cosine is even. So if we invert our angle, basically what we're doing, or in this case, it could be x, could be angle. We know that when we have a cosine function, and if this is cosine, well, not if, it's cosine of x, it's equal to cosine of negative x. Because when we rotate that across the y, or the imaginary axis in this case, or the y-axis, my bad. If we rotate that across the imaginary axis, or the y-axis, we'll get the same cosine. So cosine is even. So this is going to equal to 5.66, well, 5 point, just run that to 3 decimal place. So that would be 5.67. You factor out aj, it's going to be a plus. So that would be 5 minus 5.657. That's going to equal to a negative, sorry, my bad, that's going to equal to negative 0.657. So that's negative 0.657. And here we have that in rectangular form. We'll then convert that back to complex or polar. So we go ahead and do that. So the magnitude of our complex is going to equal to, so let's just write that. So our complex number z, and in this case we're using x. A complex number x is equal to the magnitude of x times e to the j phi. Magnitude of x is equal to the positive square root of x squared plus y squared. And our angle phi is equal to the inverse tangent of y divided by x. So we can go ahead and write that as a magnitude of 5.7 after using our expression, and an angle, we can write that. So here we can write this expression as e to the j inverse tangent y over x. That's what I'm going to do. So when we do that, we end up with a negative angle of 6.62 degrees. And as always, we can write that as 5.7 with an angle of negative 6.62. And that's in ampere. Thus, this is the phasor component, or the phasor counterpart of the signal I of t. And that's it for today's video. So I'll see you in the next one. Bye.